All right, so today we're continuing to talk about identities, specifically focusing in on the double angle and half angle formulas that have been on your identity sheet. So these are the ones we are specifically looking at today. Notice that a lot of them, there are multiple identities. And if you are interested in looking at the proofs of how we get from one to the other, those are in the book. For instance, it shows you, that this is kind of the original half tangent identity, but then it shows you how they derive both of these two, which are often a little bit more useful in some cases. So you are not going to have the same work as someone else necessarily, but because you might choose a different identity than they did, but you should get the same answer. All right, so here's the type of stuff we're going to see in the practice. Example 1, use the given information about angle theta, with theta being between 0 and 2 pi, to find the exact value of the expression. So there's a whole section like this, and all the thetas are between 0 and 2 pi. Then it gives you like a specific quadrant for each problem. So in this one, it's telling us that theta is between pi over 2 and pi, which means that we're working in quadrant 2. So that's what you're going to have to do first on these types of problems, is to draw your triangle in the appropriate quadrant. So in this case, before I even get into trying to find sine of 2 theta, I need to draw my quadrant 2 triangle, where the sine opposite over hypotenuse is 5 over 13. So this is part of a Pythagorean triple, and as I've said before, if you just know the Pythagorean triple, you don't have to show the Pythagorean theorem. If you don't know it, obviously you'll need to do it. Don't just guess. But the other side in this case is 12. Remember that in quadrant 2, sine is the only one that's positive. So you can either mark this with a negative to help you with that, or you can just remember to check all of the answers against the All Scholars Take Calculus, because only sine should be positive in quadrant 2. So this is our regular theta. We're then trying to find the sine of 2 times theta. So the double angle for sine only has one choice, so that narrows down our options. So we're going to go ahead and do 2 times sine of theta, which was given to us, 5 over 13, times cosine theta, which we obviously can calculate. So now that we have the triangle labeled, adjacent over hypotenuse would be negative 12 over 13. And so then we are just going to multiply that through. So 2 times 5 over 13, and then times another fraction, negative 12 over 13. All right, and we get negative 120 over 169, and we should always be leaving everything in simplest fraction and radical form. I'll show you some exceptions where we're not going to have to always simplify all of the radicals, because sometimes in this section we're going to get those radicals within a radical, which would take a really long time to simplify, and so the book leaves them as well, not just me. So negative 120 over 169 for that one. Now, cosine 2 theta, we've got several different choices, and it really doesn't matter what choice you make. I usually choose the one that doesn't deal with negatives if I can help it. So I'm going to choose the 1 minus 2 sine squared x, because sine theta is what we were given. I know that it's right. I didn't calculate it myself. So there's just, less of a chance of mistake if you use what they're giving you. So that means we do this. And when I square 5 over 13, that gives me 25 over 169. So multiplied times 2 then is 50 over 169. And so, of course, 1 is 169 over 169. So when I take 169 minus 50, I get 119 over 169. And there's my answer for that guy. Tangent to theta, one option here. So 2 tangent theta minus or divided by 1 minus tangent squared. So I need to look at my triangle again to make sure that I know what the tangent of theta is. So tangent is also going to be negative in this quadrant, and opposite over adjacent is going to be negative 5 over 12. So plug that in here, and then I'm going to plug it in again down in the denominator, but squaring it. So on the top, then the 2 and the 12 are going to reduce. So I've got negative 5 over 6 in the numerator. In the denominator, when I square this, that's going to give me 25 over 144. So then I've got 1 minus that. So 144, oops, helps if I actually type it in correctly. So that's also going to give me a 119, but in this case, now my denominator is 144. So negative 5/6 divided by 119 over 144 is the same as negative 5/6 times the reciprocal. So 144 over 119. Looks like I've got a bunch of prime numbers there, so I'll be sure by using my fraction button, but we may not get anything to reduce. We may get some big numbers here. So multiply these through 149 over 1. Oh, that's 144, isn't it? Sometimes I can't read my writing when I use this software. Okay. There we go. So negative 120 over 119. All right, so far, so good. Really just kind of a lot of plugging in and simplifying, not a lot of brain power that we've had to expend. When we get to the half angles, you do have to be careful on the half angles, because what we have to do that we don't have to do with the double angles is we have to check the quadrant. So if we know that theta is between pi over 2 and pi, that means that theta over 2, I would have to divide everything by 2. So that means that my half angle is now going to be between pi over 4 and pi over 2, which means that I know that my answer should be positive here. The reason why that's important is because you'll notice on all the half angles, the formulas have plus or minus. So you have to make the decision as to whether it should be the plus or whether it should be the minus. It's not both. That's not why it's in the formula. It's in the formula because you have to decide based on where theta over 2 would be located. And in this case, because theta over 2 is going to be in quadrant 1, I'm going to choose the positive version of this square root. And again, we don't see plus or minuses, any of that on the double angles, so you don't need to worry about that with double angles, just half angles. So I am going to use the positive version of the formula, and it's going to be 1 minus the cosine. So cosine, we said, was negative 12 over 13. And then we've got that divided by 2. So, of course, minus a negative becomes a positive. So I've got 1 plus 12 over 13, which that's 13 over 13 plus 12 over 13 is 25 over 13. And then dividing by 2. So that means that this is really the square root of 25 over 26. And for this one, I can simplify the radicals. So obviously the top is a perfect square. The bottom, it's 13 times 2, so it can't break down. But I do need to rationalize my denominator here. So that's going to give me 5 radical 26 over 26. All right, so we've now gotten practice using all of the double angles and one of the half angle identities. In example 2, we're taking a little bit different approach. So it's giving us one item to find, and it tells us we have to use a half angle identity. So what this is telling us is that I have to figure out, okay, 22.5 is half of what? And I rewrite it in that way. So 22.5, of course, all I have to do is double it, is half of 45. So this is equivalent to writing it this way. And so when I write it this way, I can see how it lines up with my half angle identity. So cosine here of my half angle, it's going to be plus or minus. And again, I decide based on the angle itself. 22.5 is in quadrant 1, so I'm going to use the plus again. And that's going to be square root of 1 plus cosine of theta. So theta is 45 and then over 2. So it allows us to find the exact value based on unit circle values there. So 1 plus cosine of 45 degrees, and then I'm going to divide that by 2. So cosine of 45 degrees is radical 2 over 2. And then I need to simplify. So simplify in the top first. So turn this 1 into 2 over 2. So that's going to give me 2 plus radical 2 over 2 in my numerator. And then I need to divide by 2 again. So then I've got 2 plus radical 2 over 4. If I give the numerator and the denominator each their own symbol, then I've got this with a plain 2 in the bottom because square root of 4 obviously comes out evenly. Here's what I'm talking about where we've got radical within a radical. Yes, technically you can simplify those using fractional exponents. You are not required to because that's not the purpose of the question. And so you can leave them like this. Sometimes, like if the denominator wasn't a perfect square, we would leave that as well because rationalizing into a double radical is not going to be necessary. So if you end up with radicals within radicals, you can leave those. You do not need to try to simplify those. All right, next one, same idea. So really I just need to double 3 pi over 8. So if I multiply that times 2, it's 3 pi over 4. So this I'm going to rewrite as the tangent of 3 pi over 4 over 2. So now it's in that half angle format. I can go up to my tangent formula. And in this case, I have a bunch of choices, and which choice you make is going to depend upon the situation. So if your formula, like if you were like working in an identity and you were going to be squaring something, then maybe you would choose the square root, because the squared and the square root would just undo each other. So there definitely are cases where you might choose the first one. In this case, because nothing's squared, I really kind of want to avoid the square root so that I don't have to worry about rationalizing. And as far as which of these I go with, it certainly does not really matter. You can kind of choose that as you desire. So I'm going to do the last one. I'm going to do 1 minus cosine of theta and 3 pi over 8. This is less than a half of a pi. So I am in quadrant 1, so it's going to be positive as far as that goes. So I know that the overall answer should be positive. I'm going to plug in 1 minus the cosine of 3 pi over 4. And then in the denominator, I'm now going to have sine of 3 pi over 4. Because again, in this format, the x, if you will, is 3 pi over 4. Right in there. So I'm just plugging that into both places. 3 pi over 4 is the 45-degree reference angle in quadrant 2. So in quadrant 2, cosine is negative. So this is going to be negative radical 2 over 2 that I plug in there. And sine is positive in quadrant 2. So this is just going to be plain radical 2 over 2. And then I work to simplify. So this is going to become a plus. And then when I get a common denominator, that's going to give me 2 plus radical 2 over 2, just like in the last one. But this time I'm dividing by this entire thing. So set up my multiplication by the reciprocal. These twos are going to cancel out. And then I'm going to need to rationalize because I can't leave that guy in the denominator. So 2 times radical 2, radical 2 times radical 2, and then in the bottom, radical 2 times radical 2. Notice you could factor out the 2 to show that it cancels, but since they're all divisible by it, I would leave it and just get rid of the 2's. Again, that only works because all 3 terms have a plain 2. So these are all going to become 1's. And typically when we write answers that have a whole part and a radical part, we put the radical part second. So we'll kind of switch the order here for our final answer to be 1 plus radical 2. All right, so that gives you practice with each of, we've used the half angles for each and the double angles for each, so you can see how those work. Now we're going to work on some establishing of the identities. So remember, we have to use all those strategies that we talked about, and we are trying to work with one side only and to get the manipulation to match the other side. So typically I'm going to start with the side that has the double angle or the half angle. So I'm going to start on the left here in A. And I know that this is going to be the sine half angle, but then I need to square it. So I'm going to rewrite that just so that we make that clear. So half angle squared is how I can rewrite that. Those mean the same thing. So I go up to my half angle, and here is the formula that I'm going to substitute in. It doesn't matter whether I put in the plus or minus because I'm going to be squaring the square root anyway, which is going to obviously get rid of that. So square root of 1 minus cosine x over 2, and then squaring that, which then of course gives me 1 minus cosine x over 2. So from here, I am going to separate out my fraction. So this is going to give me 1/2 minus cosine x over 2. And when I look at this guy, notice that it really isn't in fully simplified form either. So you could separate this out to being, the secants would cancel in the first one, so that would be 1/2, and then this one, 1 over 2 secant. So I know that cosine and secant are reciprocals of one another, which means that I could rewrite this, trying to decide where to put it, as 1/2 minus 1 over 2 secant x. And then I could put it back into a fraction by getting a common denominator. So I would need to multiply both of these terms by secant x. So that would give me secant x over 2 secant x minus 1 over 2 secant x. And then simple combining of the fractions would get me to the right side. So I have shown that those are the same. All right, next one, cotangent of u over 2, and trying to get that to equal this in terms of sine and cosine. So cotangent, of course, is the reciprocal of tangent. So this is going on the left side to be equal to 1 over the tangent of u over 2. And then I have several choices on the tangent half angle, but I want one that is going to, when I reciprocal it, have the minus on the cosine and the sine by itself. So that's this one. So I'm going to do 1 minus cosine u over sine u. So 1 minus cosine u over sine u, which then, of course, becomes 1 times the reciprocal, which, of course, now is looking like my right side. So not too terrible. I feel like they're pretty standard, just using new identities, but nothing more complicated than what we've been doing. C is going to be a little more difficult because I've got that 3 theta in there. And so that's not a double angle. That is actually giving me 3 times an angle. So this one is going to require just a little bit of trickery. Anytime you see a 3 or a 4 in there, you're going to have to do just a little bit of extra thinking. So I don't want to mess with this right side because, again, when we were just working with reciprocal and Pythagorean identities, we often started with the more complicated side. But with our sum and difference, half angle, double angle, we actually usually start with the simpler looking side. I'm going to start over here, and I'm going to make that left side equal to tangent 2 theta plus theta. So the reason I'm doing this is because I'm in the double angle section, and it seems like I can use my sum and difference identity then in order to simplify this. So tangent, excuse me, the formula for when I have a sum of the two is, it simplifies into the tangent of the second plus the, tangent of the first, sorry, so 2 theta, plus tangent of the second, so tangent theta. And then on the bottom, it's 1 minus tangent 2 theta times tangent theta. So when I look at those, I then can use my double angle identities in here. Now, tangent has several different double angle identities. So as far as what you want to use to make the substitution, we're going to have to look and kind of decide here. So I've got these 3 to choose from. Or no, sorry, I don't. That's half angle. What am I talking about? I just have the one, which is kind of nice because having choices makes it sometimes a little bit more complicated. So for all of those double angles, I'm going to put 2 tangent theta over 1 minus tangent squared. So this guy right here is going to become 2 tangent theta over 1 minus tangent squared. And then this guy, of course, is just still tangent theta. And then I do the same thing on the bottom, 1 minus, and then it's going to be this whole thing, 2 tangent theta over 1 minus tangent squared theta. And then that's going to be multiplied this time by tangent theta. So lots of simplifying to do in this case for how I'm going to, excuse me, get this to work. So on the top, I am going to find a common denominator. I probably better write smaller. So I'm going to need to multiply this by 1 minus tangent squared theta and this as well. So I haven't changed anything because I multiplied by 1 there. So this on the top is going to give me 2 tangent theta plus tangent theta minus tangent cubed theta, which is looking good. Then in its denominator, we've got 1 minus tangent squared theta. So this is all just the actual numerator. And then for the denominator, I've got the same idea. This is in the numerator itself, so that's going to be, this 1 is going to need multiplied by the 1 minus tangent squared. So I'm going to do 1 minus tangent squared theta, and then it's minus this fraction. When I multiply this tangent, it's going to be minus 2 tangent squared theta, all divided by 1 minus tangent squared. So I do not have a lot of room left to write. I'm going to try to get it in here. So I can combine like terms here in my top fraction, and that gives me 3 tangent theta minus tangent cubed theta. My denominator, if it'll let me write the whole thing, is 1 minus tangent squared. Then I'm going to multiply times the reciprocal, which is going to be convenient because my 1 minus tangent squareds are going to cancel out. My numerator here, when I combine like terms, I do have 3 of those. So it's 1 minus 3 tangent squared theta, which is exactly what I'm wanting in my denominator. So these are going to cancel, which is now going to give me my right side as I wanted. And we have established the identity with no room to spare. All right, hopefully those make sense. They are a little bit time consuming, so just be diligent. I did not assign a ton of problems, but I did assign you practice with each of the identities for sure. And just let me know if you have questions.